Thank you for joining this session of Shadow the Scientist. My name is Jamika Marshall, and I am pleased to serve as the Shadow the Scientist Programs Manager. In this session, we will be joining the Gemini North observing team for exploring the universe with the Gemini North telescope. I'm your overall session host, and we have several science hosts, Erin Figura and Emily Peavy. Now, we are also joined in the control room by some amazing science staff, including Jesse Ball, Leila Alamos, Christoph Clergion, and Thomas Snyder. Shadow the Scientist is an initiative that is brought to you by an amazing team at the University of California at Santa Cruz. Now, the International Gemini Observatory consists of twin 8.1 meter diameter optical infrared telescopes located on two of the world's best sites. The Gemini North telescope is located here on Hawaii's Maunakea, which is a part of an international community of observatories that are built to take advantage of the superb atmospheric conditions on this long dormant volcano, which rises about 4,214 meters into the dry, stable air of the Pacific. By incorporating technologies such as laser guide star adaptive optics and multi-object spectroscopy, astronomers in the Gemini partnership explore the universe in unprecedented depth and detail. Now, this session is indeed being recorded, and you can find it on our YouTube channel afterwards. Now, I'd like to welcome our science hosts, Emily Peavy and Erin Figura. Emily was telling us what we're seeing here on the summit. And so here, right here with my cursor is Gemini, and the dome is open for science observations. But Emily, take us again quickly through what else we see here.
Okay, the mouse that you have the cursor on is the UH 2.2 meter telescope. Then next to that, on the other side of Gemini, is the Canada-France-Hawaii telescope, or CFHT. And then we have the NASA Infrared Telescope Facility, or NASA IRTF. And then immediate in the foreground, we have the Keck twins of Keck 1 and 2, which are the largest of the optical observatories at the summit. Now, while the Keck twins are the largest optical telescopes, Gemini is one of the largest single-piece mirror telescopes. So while the Keck's mirrors are segmented, Gemini is one single structure. However, we're not technically the largest. Subaru was built the year after us and is 0.1 meter bigger than us.
They're 8.2.
Yeah, they're at 0.2. Yeah, yep. And now we're using their camera. Although I always want to emphasize that as much as we joke about that and stuff like that, all the observatories on Mauna Kea, they do work together as collaborators more than we compete with each other.
Oh, yeah.
There might be some areas, like sometimes with a little bit of technology or instrumentation, we might have a little bit of competition, and when it comes to the science, we are definitely working together.
Yeah, and to a large extent, we are complementary in what we do. There's not, I mean, we have different parts of the spectrum we're looking at and different tools that we can use. And there's certainly a lot of overlap in places, but the way the different telescopes operate, the way you get time on the telescopes varies. And so I think that a lot of the rivalry is more the good-natured kind of, we will tease them, they will tease us, but it's not really competitive in any way. We all want to see everybody else succeed is basically, I think, a best way to summarize that.
I like that. That feels good because I know some of our listeners, our watchers who may be joining us virtually right now, or those who may watch this recording later. Perhaps you've been in situations, especially in academia, where things are super competitive and it takes the fun away from what you're doing. And I know for me, I really enjoy your enthusiasm and the passion that you share with us. And it's
clear that you enjoy what you're doing, and that camaraderie extends to the entire community.
It
That's
does.
something that's pretty
In
incredible
fact,
and special.
one of the things that we do on a nightly basis is the night staff all communicate with each other. Um, we have Slack channels that we use to communicate, to update each other. Um, Usually, we're talking about problems, so weather issues at the summit. Somebody will, will note that we've got some fast rising humidity and uh, some fog showing up over the eastern plateau, and I will warn the other telescopes in case their cameras haven't seen that. We have a lot of cameras that are not attached to the telescope themselves, but like that Subaru image there, are designed to give us a view of the night sky surrounding us. So if actually I can do a little share here,
Yes, please.
I am going to find ha, my stuff is missing.
No worries, no
Give
worries.
me
And I was just thanking everyone in the chat. Thank you so much for letting me know about the audio issues. We were trying something a little different this time, and so we appreciate your feedback. Yes, Nikki, thank you, thank you, thank you, and welcome, Michael. Welcome, Bonnie. And if you have questions, please feel free to put those in the chat at any
All
time.
right, I am going to just do a quick little share here.
Ooh.
So this is a summary page, and actually anybody can come and take a look at this page. This page is publicly accessible. So you can see the address right up here at the top. And this is basically a status page for the observatory that is there for observatory staff, but also for researchers who are using the Gemini telescope who may be interested in triggering some observations. So if I can take you through it really briefly, you can see down the center panel here, we have a set of five actually, five summit cameras, and you'll see there's an animated loop. That loop is 15 minutes long, one image taken every minute. So we have our east camera overlooking Hilo here, very bright toward Hilo. We are shortly after moonrise, and so that's that big glow we see off to the left.
I was wondering what that big glow is.
That's that moon that we were just watching out the front window. So we've got that moonrise, and you can see that beautiful cloud layer down below us. As Jamika mentioned, the summit's up at over 4,000 meters, which is 14,000 feet. And we have a very interesting meteorological phenomena that occurs here called an inversion layer. That inversion layer is essentially a temperature switch. It's a temperature inversion in the atmosphere. And what that does is it traps moisture and everything else down below that layer.
Like dust too?
Like dust. And when you've got, a nice cloudy layer like that, it's also going to reflect any light pollution. So in that image right there, sort of where those clouds are roiling away, down below that's Hilo, that's us. It is very cloudy, and it's been raining here in Hilo tonight, which does not really narrow anything down for Hilo.
Common.
It is. Oh, that light pollution though. I know, Emily, in your outreach and other talks that you do with the public, light pollution is something that you all have definitely addressed, because it's detrimental not only to scientific research that needs dark skies, but just for those of us who want to go out and enjoy being under dark skies. But it seems like here in Hilo, we've the lighting around the community really helps to decrease the effect of light pollution. Can you tell us a little bit about that?
So light pollution in most places of the world is just becoming a rising and rising problem. And that is just having too much ambient light at night that we astronomers, we never like it because it bleeds into the sky, but there's also a lot of studies that go into how too much light all the time it's detrimental to our health, and it also is a detriment to wildlife and wildlife behaviors. So we're very, yeah, and we're very, very lucky here in Hawaii, where there are uh we are very proactive in reducing the amount of light
Yeah.
pollution, and that is a big benefit to astronomy, but that is also very a benefit to our lives, to us as humans, and to even our wildlife. I know my mom volunteers with sea turtles, and they're one of their big things for sea turtles is that when sea turtles hatch, humans are not the only stargazers. Sea turtles will go towards the ocean, and they've worked out that this when a sea turtle hatches, that it finds the ocean because it looks for the light of the stars and the Milky Way reflecting off of the water of the ocean, and so they'll go towards the ocean if it's nice and dark. However, if sea turtles are nesting, and sea turtles return to the same beach. So they were born on a beach, they go have their lives, and then return to the same beach for a nesting site. And say between that time, if there is a road that was constructed near a beach sort of thing, and that road has headlights, and now the sea turtles hatch and they see the light shining on the road, they think that that's the ocean, and then they'll go towards the road.
Oh,
So yeah, and
no.
so just being mindful of where you are putting lights, and it helps everything in our environment around us, especially your locally grown astronomers. So we're the sometimes the most finicky of wildlife.
That's
And we're
true.
lucky to have a very very cooperative community here. But as you mentioned, it's sort of an initiative across not just our island, but
Yeah.
all of the islands to help preserve the environment. At the
Absolutely.
summit, our principal forms of light pollution are moonlight.
Yep.
I mean, what you're seeing our light pollution now. This is a very bright environment. I want to draw your attention. Actually, I was watching in the west camera here. This is one of those telescopes uh, that was not visible from that Subaru view. That is the United Kingdom Infrared Telescope, or UCIRT. And um, one of my favorite little, some people like the cat videos. I love telescope time lapse videos. So, getting to watch the telescope move, and you can see it jogging back and forth there, and then do a full slew around to the other side of the sky. But we have four cameras pointing toward the horizon in four directions, and we also have a fifth camera that is pointing up. These don't cover the whole sky, but they cover enough that we can get an idea of um, of weather conditions that may impact us. Tonight, it looks like a perfect night. We have no high cirrus clouds. We have no absorption of starlight. The uh, the inversion layer looks really solid and well defined. It's down there around 9,000 feet. Eyeballing it looks like it's around 9,000 feet. For those of you who wonder how I can tell, it's because 9,000 feet is sort of its normal place, and I recognize that that's about what it looks like. Um, what we'll see when it rises, that's always something to be worried about, because as it rises, all of that humidity comes up too, and so we'll watch, in this north camera, and in that east camera in particular, and we'll see those clouds come up and even come up over the east plateau here, and that's when we really start getting nervous about taking care of the telescope. It doesn't mean we close right away, but it means we think really carefully about what we're doing, and we look at how fast it's been changing. And then the operator, Layla, tonight will take the appropriate precautions. But with all of this, we were talking about what the operator is doing. I'm going to
That's
stop
right.
the share
That's right.
here again.
Before we
Yeah,
get
by
to
all means.
Layla, could we respond to a few questions? And I see, Emily, you've already responded to one question from Vonnie. We have two questions from Vonnie. The first one is, I see, sorry, there's another one. What role can citizen scientists play in limiting light pollution? And Emily, you responded, the Globe at Night is a fantastic citizen science project that focuses on light pollution. So, and you dropped the link in the chat. I'm going to share my screen. And while I do that, can you tell us quickly about the Globe at Night?
Yeah, so Globe at Night, and you can see the site here. This is globeatnight.org. This does just certain operation runs where during a certain time period each month, they will walk you through how to find a constellation in the northern hemisphere sky that should be seen across many places on the globe, and teach you how to find this constellation, and then teach you about some basics of light pollution and rating the level of light pollution in your sky. So we'll teach you how to find this constellation. And then when you find this constellation, you are identifying what is the brightest star that you can see in it and what is the faintest star that you can see it in order to help gauge the level of light pollution in your specific neighborhood. And then when you enter this data, this goes into a larger database in order to track the areas of light pollution across the world and across the nation in order to see which areas are having more adverse effects of light pollution than others.
And we can see here, thank you, Emily, we can see here how the steps that you would need to take in order to do that. Starting with number one, when you make the observations, where are you when you make those observations? Did you use a sky quality meter? Aaron, what's an I'm sorry, Emily, what's an SQM? Because I was going to ask Aaron.
I am going to admit that I have not actually used one. I just know of them from helping out with this.
We won't tell anybody.
But
Aaron, have you used one before?
I have just as a little bit, and basically what it's doing is it's going to make a measurement of exactly how much light is coming from the sky. So you're going to point that to a patch of, just normal sky, and it's going to give you an idea of how much energy is hitting that detector, radiating from that area in the sky.
Oh, I see. And here, the reading you would add here in magnitude per arc second square arc seconds. Okay.
So
now, if you're a citizen scientist, but you do not have a sky
Yes,
quality
that was
meter,
my
that
next
is not a required question.
Great.
Yes.
So you can skip 3 if you don't have that and go to number 4, which was how dark was the sky that night. And Emily, can you tell us a little bit how we make that decision?
So this is going to be just based off of your own observation. So you're looking at this area of the sky. It looks like we're looking towards the constellation Pegasus.
Mhm.
And so you're looking towards that area of the sky and just kind of gauging how many stars you're able to see in the sky. And here you can see like a good diagram of, okay, maybe the like magnitude 0 is like you're not seeing anything. You're not seeing any bright star. You might see an airplane. Yeah, you can tell it's an airplane because it's blinking. But then magnitude 2, okay, maybe you're seeing the brightest of the stars. Magnitude 3, you're seeing some of the main bright stars. Oh yeah, Saturn was even is even in this field of view as an example. And Saturn, like planets are usually sometimes if you don't see stars, you'll still see the planets. And if you're not even seeing the planets, then that's a very, very hard either light polluted sky, or it might be a cloudy night. And sometimes that is a factor for it. Sometimes, and as we were talking about before, we often talk about light pollution in other areas that we're talking about pollution. We're thinking about human caused light pollution, but there are also natural sources of light pollution, such as a full moon. The full moon might bring down your that magnitude scale to like a 1 or a 2.
Oh yeah,
yeah,
particularly in the direction of the full moon.
Absolutely. Well, it seems like this is pretty easy to use. Very clear directions. There are 5 steps, and then you just submit your data when you're ready.
Yeah.
All right. And this is a NORLab program.
This is a NORLab project as well. And also, I believe through this site, there's also recommendations that if you are looking to be an active citizen in your area to help reduce light pollution in your area, there's advice that you can be taking on about restricting light use in your area. If you are feeling so inclined to even be talking to your local government about, hey, this is an issue that I am concerned with, and this is what the ways that we want to limit it. Things that Hawaii has done largely because of astronomy, but then it's also, we are very interested in this movement has continued through Hawaii's interest in helping preserve our sky and keep light down through other projects such as natural wildlife. But Hawaii, when if you come to Hilo, especially, you'll notice that we don't have a lot of street lights on the highway at night. If you need to use your headlights for safety reasons, of course, which you should be anyway, and that reduces light pollution. And when you are in a populated area, you'll notice that our lights are set up a bit differently. We have LED lights or very specific halogen lights that are designed in order to be limiting the light to a smaller pool. And that light source is also set up so that you could be easily subtracting it out of astronomical observations if astronomical observations are catching that light.
And I think one of the other things to do is there's a lot of things you can do as a private citizen, and you think, well, one person doesn't make a lot of difference, and that may be true, but a lot of one persons make a lot of can make a big difference.
Yes, we
You
do.
know, things like, making sure that exterior lighting is downward facing, that you don't use it any more than you have to. It is, when you see, if you have security lighting, if you can actually see that light and it looks blinding to you, it's not going to be good for your security because that's killing your night vision. It's kind of interesting that a lot of things you want outdoor lighting for, they work best under the same conditions. Downward facing lighting, putting light on the ground is a lot better than light that is going to be directed upward and outward. I'm a person that loves like landscape lighting and everything. I think that's gorgeous, but doing it responsibly, keeping the light down is a big deal. Trying to avoid as much outdoor lighting as you can, and just making small differences. And when you look and you see some of these, you can look and see images. If you've ever flown across the country at night and you see those, the lights of cities, it's gorgeous, but it's also startling how few dark patches there are.
That's right. It really is. And that leads into another question from Bonnie. How will the increase in light pollution, affect future observations? And you were just
Yeah.
talking about that
Yeah.
a little bit.
The light pollution, essentially what that light pollution is going to do from the sun, from the observatory perspective, from the astronomer perspective, the more light pollution you have, the harder it is to discern the signals that you're trying to measure from noise. When you look at the night sky, you're not seeing, as much as you might think you are, you're not seeing pinpoints of light against blackness. You're seeing pinpoints of light against some kind of gray. Even in a clear sky, you are not seeing a perfectly black background. There's enough atmospheric scatter that there's always going to be some of what scientists call noise. And trying to discriminate the signal from the noise is what's really hard. And I think a great example of this is if you ever look at the night sky near the full moon, and you might look away from the full moon and see
Yes.
plenty of stars. When you look near the full moon, you're not seeing anything. Maybe one or two of the brightest stars, but you can't see anything else. Those stars are still there. The problem is there's so much scattered light from the atmosphere that you cannot distinguish the starlight, which is really faint, from that scattered light. So it gets lost in the noise. That's sort of this kind of the overview problem of what our issue with light pollution is. It just makes the faint things harder to see.
And then what about the number of satellites is another
Oh.
question here, the increase in the number of satellites. How does that
That's-
affect your observation?
Before, can I jump in with that question?
Oh, go, Emily.
I also want to answer that question, not also from an observatory perspective, but also from a human perspective of observations, because all observatory observations start with human observations, with us wanting to have and having a connection to the sky.
That's right.
And with the increase of light pollution, with more people growing up in environments where you straight up just can never see the sky, or the sky itself, this natural phenomenon is a luxury. It is not something that is accessible to everyone.
It's a
Then
privilege.
people
It is.
lose their connection to the sky. And when people lose their connection to the sky, they lose their curiosity about things to the sky as
Absolutely.
well. And sometimes that curiosity gets replaced with mistrust to the science as well. And so I think all of these things end up playing into each other. So even like building up and making sure that you're building up little spaces that you can ensure that people around you are able to see the stars to then have a connection to the stars.
It's,
very important.
it's the astronomical version of touching grass.
Exactly.
Well,
But I mean, I taught physics and astronomy for quite a few years before I came to the observatory. And one of the things I would regularly teach people in my intro astronomy class who would come in from the larger cities, who were coming in from Minneapolis, St. Paul, were coming in from Chicago. In Chicago, if you see a star on a clear night, that's amazing. So the sky just ceases to be a thing of interest. And I had actually over the time I taught 3 different students who came from those big cities and just never had any relationship with the sky, who decided while they were there that they were going to start studying astronomy. Because they got out there and they came out to our campus observatory, and I said, here's the sky from this rural Iowa area. And they were shook. I mean, they had never even looked up.
I believe
Because
that.
they had no reason to look up. When you're in Chicago, it's sort of a sodium yellow, that street light yellow glow.
I love that description, that sodium
Sodium
yellow.
sky.
I know exactly what you're
Yeah.
talking about. I can picture
So,
it so much.
And obviously Chicago is huge, and that their light pollution problem is staggering compared to many other places. But I mean, that's an extreme example, but it's exactly an illustration, I think, of losing touch with part of the world around you.
Well said, well said. Thank you for that. And then so as when we get to astronomers now, as they are trying to do their work, this increase in the number of satellites, getting back to that next question with
Yeah.
Bonnie, so we don't have just light pollution to worry about. The satellites going up, the trains,
Yeah.
a series of satellites going up. And I was reading somewhere that in the next 10 years, if we keep on pace with satellite launches, that when people actually look up at the sky, there's a 50-50 chance that what they're looking at are actually satellites high in orbit and not actually stars. So I would be very curious to know, Aaron, for observing, like, Layla's role, and I believe Jesse's role as the observer there in the control room tonight. How do you deal with satellites crossing the images?
I'm gonna go back to our cameras here for just a moment, because I noticed.
Oh, yeah.
So in that north camera, there you'll see that low one that goes by.
Yeah.
That's an airplane. But the stuff up here, the stuff up high there, those very fast
Yes.
streaks, those are
Mhm.
satellites.
Yep.
My
Wow.
my youngest daughter is spectacular at finding satellites. She'll go outside in a dark sky and she'll look for 2 minutes and she'll have one.
Yes.
It's and the longer she looks, the more she counts. So dealing with satellites is rough. When we're doing imaging, at least they're easy to identify. When we're doing one of our science data collection techniques is to make pictures, to make an image. And usually that's very obvious. When you've got a satellite crossing the image, there's a white streak right across the image. And depending what you're using that image for, if you're looking at one small spot on that image, then you may not care about what happens over on the periphery of that image.
Exactly.
But if it goes across the middle, where where what you're looking for probably is, that makes that image worthless.
Wait,
And
it
that's
can't be subtracted in any way?
no, because they're usually so bright that essentially they're saturating that line across, so you can't easily remove that. We can remove a lot. Cosmic
Right.
rays, noise. There's a lot of things we can do in our data reduction process to get rid of things that show up that we don't want. But a satellite it's just too much. And if we have spectroscopy data, then it's a lot harder to identify because you don't have that picture. You have the spectrum that was collected, and it's a lot harder to figure out that that image was tainted in the first place.
Oh.
Now, the good news about that is usually when you're doing spectroscopy, you're looking at a very, 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 such a tiny little window that it's much harder for satellites to be an issue.
That sounds good. Okay, that's enough.
That sounds good. That
Yes.
helps. The other thing that helps is, we've got some companies that have been working with the astronomical community to try to um, decrease the reflectiveness of their satellites.
I read
If
about
the
that.
satellites don't reflect light, then they're less of an issue for us. The problem is if those satellites are using solar panels, those solar panels are going to be reflective. They're going
Yeah.
to be like they're going to be like big mirrors essentially. They're not mirrors, they're obviously absorbing light, but they're also reflecting a lot. And so when you're actually seeing those satellites, that's really what you're seeing is you're seeing light reflected off their solar panels.
That's
And that's really hard to get rid of.
So with that increase potentially happening in the future, hopefully we'll have more and more collaborative efforts to bring the reflectivity or the albedo
That would be good.
of those satellites down so that there's less destructive interference with.
And the problem, of course, is that those approaches typically are going to cost more money.
Yes.
And that's going to be a lot harder for a lot of, a lot of more developing nations, maybe less interested in or less able to forget interested, less able to
Yeah.
do that. And you've got enough companies here, even in the US, that are just not interested in that expense.
Mm, mm.
I think it's as an astronomer, my knee-jerk reaction to the amount of satellites around us is always like, oh man, we do have a lot, and they're always so bright. And some of them are like sometimes intentionally being bright. But sometimes there are satellites that are doing important purposes, like
Absolutely.
providing access to
Yes.
important resources to rural areas. And our observatories also need to be constructed in rural areas. These people who are benefiting from these things also end up being the
Yeah.
neighbors of our
That's a good point.
observatories. But I'm also in a position of the if you're going to have this many satellites up there, they need to be a public good, and they need to be a public good that is easy to be accessed by the people who need to be accessing it. And me personally, I don't put a lot of trust into a profit-driven company for for doing that. And that's all I'll say as an person
it
who's
is.
employed right now.
And I think there's a lot of good point there in how we look at them. Obviously, we put satellites up for a lot of good reasons, some poor reasons, but a lot of good reasons, and they
Yes.
help a lot of people out. Whether they are providing satellite imagery for weather prediction, for climate tracking, whether they're providing internet for rural areas, and those are all good things.
Absolutely.
And so the issue here is not that we hate the satellites and we want to get rid of them, but they do pose a problem for us that we have to work around. And when we've got data that's contaminated with those, that's time on sky
That's
that
right.
we don't get back. That's wasted. And as we see that problem, just increasing over time. So,
Mm.
will we be able to come up with some ways through data reduction to help get rid of that? Yeah, maybe. But I mean, when you're part of that is new types of instruments that won't saturate at those levels, so that if if you haven't saturated the detector along that path, then maybe you can recover some of that. But it's computationally intensive to do so. But advances are keep being made in processor speed. So it's not an impossible problem, but it is something we definitely have to watch out for.
I appreciate the hopeful tone that you left us with there.
Well,
And
I know there's some people who are looking at the approach of, well, just put all your telescopes in orbit. I'm like, well, we can't do that. I mean,
Oh,
practically
not
that's
feasible,
impossible.
honestly.
And it would take astronomy out of the hands of most people.
yes,
Mhm.
And there is a lot that can be done and has to be done from the surface. So it's a matter of figuring out how to work together so that we get the benefit that we need from the various satellites, and we still are able to do the science work that we need to do.
Yes,
Mhm.
yes, Aaron. And speaking of science, would this be a good time to check and see if we could chat with someone in the
I am.
control room?
I'm looking in there right now, and it looks like there's some active conversations going on.
I see.
I don't want to go and interrupt them just this moment,
That sounds good.
so we're going to let them.
Make sure everything's working. on the
We're going to let
telescope.
them work. They've got a. Basically, what happens in a time like this is the
Mhm.
engineering team has a set amount of time
Mm.
that they get to do their work. So they may have been told you get, this 2.5 hours after nautical twilight that you can do work, and after that we've got to get back on sky and
Oh,
do
wow.
the start on science. So I want to make sure that they are in a good place where they can talk, and I don't want to interrupt that, because the sooner they can get their work done, the better, the more capability we have online to do the science that we need to do.
Absolutely. Well, we defer to your judgment for sure, Aaron, for sure. Now, but you can tell us a bit about the roles, though.
Yeah.
So Layla Alamos, she's sitting on the left, and I believe you mentioned that she is
She
the
is sitting.
telescope
The
operator.
funny thing, when we say that she's sitting on the left, in the
Oh.
view of the camera there, can we pin that for just, let's
Oh,
see if we can-
absolutely. Yeah, yeah, yeah. Well, let's do that.
are we
Well,
there?
I think
that's-
someone needs to stop sharing.
Oh, that's someone, Aaron.
I was enjoying the view though.
All right.
That was a gorgeous view of a very moony.
All right, so
Maunakea.
all right, so in this view, there are we gotta be very careful about left and right, because from our perspective, when we go in the control room, we're standing in the room about where Jesse is, facing the right hand wall with all the monitors,
Right.
and so left means is this workstation that you see where all where those 8 monitors are facing you. Layla's in front of it. We can barely see Layla over there, but she's there.
Yes.
That's the operator. There's Layla.
There's Layla.
That's the operator station. On this side of the room, where you see these 2 chairs to the lower right, there's another workstation, another set of 8 monitors. That's the observer station. So that's the left and right that we're referring to here. So we already talked a little bit about what Layla does. She's responsible for the health and safety of the equipment, of the telescope, of the facility itself.
Wow.
And she essentially has the authority to close the observatory if she feels that anything is a threat. But that is her primary role,
Yes.
sort of the most important. But the thing she's doing most of the time is actually controlling where the telescope points and setting up that guiding that we were talking about earlier in the session, setting up those guidance cameras, those wavefront sensors on one of those
Yes.
stars to help get that perfect tracking of that star. And that's a large part of what she's doing there. When problems happen, and we do have faults, we've got a telescope here that is 25 years old. We went on Sky.
Wow.
What we went on
Year
Sky?
25 is when things start breaking down.
Yes, I've heard.
We went on Sky. I think was it night? I think first light was 1999.
Yes. We're over 25 now.
Yeah.
Last year
And
was.
a lot of our stuff, we've got a lot of the hardware, the telescope itself, the telescope hardware is that old, and a lot of the systems are, range in ages from that old to perhaps replace newer. A lot of our software, a good chunk of our control software is that old. So problems happen. We have, what we call faults, almost every night. If we go a night without a fault, we are, as a night staff, as an operating crew, we're really happy about that. But the operator is going to be in charge of resolving those. And there's a lot of things that we can solve as operators right on our own. There's a lot of things there are some things that we can't. And so some things we will have to call in outside help. We'll have to contact engineers to take a look at it, some of the programmers to take a look at things. And And on the worst of conditions, of course, we may find that we can't do anything to resolve the problem. And we actually have to perhaps stop using an instrument, or in the worst case scenario, close up the dome because we can't operate the telescope anymore. That's very rare. Most of the time, Layla's going to be over there and solve the problem, and we're going to be back in operation with hopefully very little time lost to that fault.
That sounds
But
great.
that's our role. Watch the
Mhm.
weather, watch out for safety, fix problems, slew the telescope, and set up guidance. That's the bulk of what the operator is doing.
And what's the other role?
So the other role is the observer. As the operator is focused on the telescope and the equipment, the observer is focused on the
The
science.
science, yes.
So Jesse is actually our observer tonight. He's actually heavily involved in this engineering task, so he's kind of not acting as the observer right now.
Of course.
But so what he's going to do, what the observer is going to do, is look at the science that we have, the possible science that we have to do for the night. He's going to monitor the weather conditions, looking at those web cameras, looking at some of those other plots that I did not explain on that web page
That's
I've been
all right.
sharing. And he's going to evaluate and pick the best science that we can do for the weather conditions we have. He's going to set that up, and he's going to let Layla know about that. And she will actually point the telescope to that new target. She'll set up the guiding, and then turn it back over to the observer, to Jesse tonight. And then Jesse will actually start the observing program that's going to actually collect the data. So the science that we do is done for the data that we collect is done for astronomers all around the world.
Yes.
And you, wherever you are listening, frankly, you can propose a science, an observation that you think would be a very cool thing to do. The problem is time is limited. We're already oversubscribed by a factor of at least 4.
Wow.
I don't remember our oversubscription rate off the top of my head, but basically what our TAC, our time allocation committee, or telescope allocation committee, all observatories have a TAC. Some of them call it time, some of them call it telescope. I never remember which one we are.
They both work.
They both work. They're
Since they
both the
start
same
with
thing.
T.
It's the TAC. The TAC is a group of astronomers here at the observatory who will evaluate the science. They'll evaluate the proposal, and they'll look and say, they'll look at this from the perspective of how likely is it? How likely is it that this is a question, that this is a good question? Is this a question that is going to tell us something about astronomy?
Yeah.
Is this a question that this telescope can solve? And is this and then how much time will it take to do that? And is that a good investment?
Ooh.
And so that's kind of what that's kind of the calculus that they're doing to evaluate which proposals get approved. And they rank these, and they say these are the highest priority, these are the lowest priority. They get ranked in terms of what kind of weather conditions they need.
That's right, because you do have a range of conditions that you can propose for.
Exactly.
From poor weather to needing something that's pristine.
Exactly. So if you have a really, really bright target, a really bright source, then a night like tonight where we've got high light pollution from the moon, that's not a problem. Or even a night that's got a lot of clouds, we may be able to see that and track that and collect data through the clouds. Other science may require just the very darkest, very clearest skies. And so all of this is evaluated. And it's not just one or the other. There's a whole range of values. And it's not just one bin of good conditions or bad, but it's a bin for light, a sort of a range for light pollution, a range for clouds, a range for water vapor, a range for atmospheric clarity, what we call seeing. So all of those things we evaluate the science for, and we sort of rate it. And then what the observer is going to do, he's going to look at what the weather conditions are and find the best science that fits that for the night. And if you'd like, I can show you a little bit about what that process looks like.
Yes, please. And I was going to also ask, even though they are busy in the control room having definitely important conversations for the engineering that they need to get that they're testing for right now, is there a way we could possibly see one of the screens that Layla's using?
Yeah, let's show you a little bit about.
Hey, Layla.
I'm going to show you a couple of screens here as soon as I. All right, let me.
And I will unpin the control room right now. So
Okay,
we can
thank
share.
you.
Yes, of course.
All right, so this is. I'm going to pull this sort of front and center. This is what we call the TSD, the telescope status display. And actually, I'm going to shrink the window behind it to try to clear out some of the confusing stuff that we. There we go. That's a little bit less confused.
Yes.
We have the operator. The operator has 8 monitors, and each of those may have multiple desktops on it. I've never counted exactly how many windows we have open. It is kind of a ridiculous number. But this screen here is showing us the conditions of the telescope and what the telescope is doing right now. And probably the sexy part, as you were pointing out, is the light path.
Yeah.
So we have a schematic here of the telescope. This is a Cassegrain focused telescope. So we have the primary mirror, that big 8.1 meter mirror, 8.1 meter or about 26 feet. I like to tell people around the island, for comparison's sake, it's about 2 Toyota Tacomas long.
Oh, that's good. That's
Wide
good.
from edge to edge.
We can all
agree,
that,
you know. Tacos are the official vehicle, I believe, of the island. But that's that primary mirror right there. So we can see light coming in. I'm betting. Oh, you can't see my mouse.
You can actually see.
So you can see light coming in these from the sky, hits that primary mirror and bounces up to the secondary mirror located at the top of the telescope. That's that mirror I actually mentioned earlier. That's what's going to do a lot of the correction to help the telescope guide.
I see.
That is also going to reflect the light down through a hole in the middle of the telescope mirror. That big 8.1 meter mirror has a hole right in the middle of it. Light passes through down to the bottom side of the telescope. And on the bottom side of the telescope, we have our instrument support structure. We actually have 5 different ports on that structure for light to be directed to. And 3 of those are occupied by scientific instruments.
Right.
One of them is occupied by our calibration source, and the other one is occupied by our adaptive optics system. So what we see happening here is that light is hitting a redirection mirror. This one's a flat mirror. It's called the AO fold. It's a fold mirror is just something that bends the light path. It doesn't do any focusing. It just changes the direction. Your flat mirror that you have in the house that you look in, that's a fold mirror. So that fold mirror is going to direct light into the over here into the adaptive optics unit at 4.
Okay, and that's AO there. I see.
That's AO. And then that's going to come back to our science fold, also called the tertiary mirror. And that tertiary mirror is going to direct the light usually to either the instrument at 3, GNIRS, the instrument at 5, GMOS, or the instrument at 1, which is down at the bottom actually, which tonight is IGRINS 2. Right now it's directing it to our acquisition camera. It's getting picked off there as part of the science or the part of the engineering work that they're doing tonight. But this little diagram tells us instantly, where's the light going? Is light traveling to the instrument that we want it to? And all of those green bits there can change color. You know, they go red. That means we've got a fault in a system there.
Don't want to see that.
If they go yellow, it means that it's not in position, and that may be fine. If we're slewing the telescope, things will go yellow. That's perfectly cool. Um, let's see, the other, let me, I'm kind of gonna just sort of pick my way around this screen because looking at interesting bits. Over to the far left, you see sort of a top view schematic of the dome.
Mm-hmm.
You can see that our slit is not all the way open.
And how can we tell that?
So the telescope slit, the shutter, opens up wide, and basically, if it was fully open, we would see this line being a little bit further back, the top end, and the bottom end would be down here. So you'd have that big black rectangle would be much, much larger. The other thing that we would see, we can see, is that our vent gates, we have the ability to open up the sides of our dome to help get air motion through there, um, to make sure we're getting good seeing. Those vent gates are closed down pretty tight. Um, and I did not check what our wind condition was, but I suspect that either our wind is higher than we want it to be, the wind conditions up there, or they just need absolute as little air motion as possible for the engineering work. But you can see our little our windrows here telling us the wind is blowing from the northeast.
Oh, I see that. I see that. I see that now. I see. I see. So normally, of course, we would be able to potentially see some the target, and we would talk about that. But since they're doing engineering at this
Right.
point, is there? Can we look at some other images,
Absolutely.
images, and talk about some of the incredible
Absolutely.
science that happens?
So
One thing, if I can jump in real quick, since from the schematic, one of the things I think that they're working on their engineering is our adaptive optics system. And adaptive optics is such an amazing thing for ground-based observatories. An adaptive optics system can allow a ground-based observatory such as Gemini to outresolve space-based astronomy.
Yeah.
So main advantage of space-based astronomy, of the Hubble, of JWST, is that they are above the atmosphere. But our adaptive optics system is actually designed to be subtracting out the effects of the atmosphere.
Yeah.
So I think that's what a lot of the work is they're doing here. And with our adaptive optics system, our 8.1 ground-based observatory here in Hawaii can outresolve the Hubble telescope,
Right.
and we can get resolution that is on par with JWST, which is great for us being able to do follow-up observations for these more
Absolutely.
competitive
Absolutely.
telescopes.
And I think that, one of the things to keep in mind is the reason that that's possible, besides the AO system, is that it's expensive to put mirrors into space. And the name of the game for astronomy is big mirrors. And so we have our 8-meter mirror sitting at the top of the mountain. It was hard enough getting that mirror up there, but that's trivial compared to getting an 8-meter mirror into space.
Yeah.
Hubble's mirror is, you know how big it is?
It's small.
It's small.
pretty
It's
small.
little. I think it's about 4.
Thank you. JWST is 6. Why do I?
I think that's right. Yeah. So even JWST is smaller than that. And this is.
JWST was like fragile. That was like nerve wracking watching
was.
that thing
I
move
was- I
around.
was
It was like
nervous.
I think a lot of people were
Yes.
very nervous. But I mean, that's the thing. So if we can get rid of the effects of the atmosphere, then we can start to do some of the same things. Now, we don't compete with JWST. We don't compete with Hubble because they have um, they have very limited time that they're spreading around to a lot of astronomers. And if there's something you can do on Earth, you definitely apply there, because there's no point in trying to get this little tiny bit of time that's available on these 2 telescopes. And to be fair, there's a bunch of other telescopes that we have orbiting the Earth than just those 2.
That's true.
And the other thing I want to point out about space-based telescopes, the one thing that we cannot correct for is atmospheric window. Visible light comes through our atmosphere very easily. That's what we see. Near infrared light gets through a little bit worse. It's a bit harder. When you start getting to other infrared signals, they get through very poorly. Ultraviolet light gets through very poorly. It's still enough to, give you a bad burn. But compared to what hits the top of the atmosphere, nothing, I mean, very little gets through. Radio gets through fine. But, so we have these atmospheric windows. If you want to do far infrared astronomy, you can't do it on Earth. It just doesn't get through the atmosphere. You want to do ultraviolet astronomy, X-ray astronomy, you can't do it here. You've got to do it up there. So there are other advantages, other considerations why we do have space-based telescopes, but there's a lot of things that we are very good at doing, and we obviously want to try to improve our capabilities, improve our seeing, our precision, to that point. And yeah, as Emily mentioned, our adaptive optics system does a great job at that.
And I'm showing Altair
I
right
see,
there,
yeah.
and I think this is mounted
This is a
on
great
the
description, yeah.
bottom. Oh, and it actually even mentions here the wavefront sensors, which maybe it's part of what they
So
talked tonight.
if I can point out in that image, so
Mhm.
that black and blue, it almost looks like about the cargo container kind of appearance right there, sort of at center of the image. That's Altair. It's hanging off of the ISS, that instrument support structure. You can see an instrument mounted down below it. That basically two black boxes and the gray bit in between. That Altair, that blue and black box together, is a little bit less than, it's on the order of like 5 feet tall from top to bottom. So, we're looking at something that's about person sized.
Right. And
So-
we can actually see two people standing here next to
Oh,
the
wow.
instrument support
Oh
structure.
yeah, there they are.
You
Yep.
see
Yeah.
Next to the mount base.
the mount base. They're tiny. You can barely see them.
I had a hard time seeing them.
Right.
So this
Yeah.
is massive, not just Altair
Right,
itself, but the whole telescope, and just looking at the bottom of the base there with these are, 5 feet, 6 feet people, right?
Right.
Probably
Mhm.
somewhere around that.
But that design where we have those 3 instruments, sometimes 4 instruments, but plus 2, mounted at the bottom of the telescope is sort of not a unique feature of the Gemini telescopes, but it's fairly unusual. Most telescopes have 1 instrument mounted at a time. Changing that instrument out is a task that has to be done during the day. And if you're lucky, it can be done over 1 day's time. Sometimes it has to be done over multiple days' time, depending on the instrument. Um, and I should point out that you have multiple instruments because you do different things. You have instruments that specialize in visible light. You have instruments that specialize in infrared. You have instruments that are good at doing imagery. You have instruments that are good at doing spectroscopy. Yeah, I'm gonna actually. Can I grab the share here?
Oh yeah, I'm
Let's
not
do it, yeah.
sharing anymore.
Perfect.
And
I'm gonna
yes,
see.
could we go to some of the, because Gemini has
I want to
incredible
do-
images.
I wanted to come over here and you can see our science fold moving. It's going to direct light
Oh,
to Genius right
yeah.
now. So things are happening. They are switching over. I think they're switching over to the science mode here. So I'm going to
Oh,
go.
that's
We're going to see if we
exciting.
can talk to them here in a little bit.
It's wonderful that you're just talking about this, because that is a big advantage that we have, that we are able to switch instruments at a press of a button, sort of
Yes.
thing.
It
You don't need to
takes-
send someone up the mountain or take one instrument off and
Exactly.
do a different one.
To switch instruments takes a couple of minutes time, basically, and most of that time is moving that science fold mirror.
I see.
Getting that little green mirror here we see to point send the light to the right instrument. Most scientists are going to use one instrument or another, but we may be doing some visible light imaging on one, with GMOS and on one observation, and then the next observation we do that night, 5 minutes later, 10 minutes later, might be some infrared spectroscopy with GNIRS. So we have that capability to switch. And in fact, some astronomers have put together complicated observing profiles where they will actually use multiple instruments in one chunk. So they're going to go, and that happens with some rapid target triggers. So we get a supernova, a star explodes, and we want to collect as much data. We're going to do some imaging to make sure we've located the target, and then we're going to switch over and do some spectroscopy once we've located the supernova. remnant, and we can start doing some spectroscopy on that, and we can do all of that. And so there's this benefit that we have, when we talk about the different capabilities telescopes have, these other telescopes that have a single instrument at a time, that's usually to be honest with you, a more capable instrument, but it's one instrument that does one thing. And we trade off a little bit of capability for in one instrument for the ability to actually switch back and forth between 3 or 4 instruments within a few minutes notice.
Few minutes notice is an incredible ability to have, and to be able to offer those who are seeking to get the best data that they can.
Yeah.
We were at Subaru last night with the C3VO research team, Roy Gal, Brian Lameau, Joel Diamond, and Finn Giddings, and that was one thing they were talking about. Kentaro, who was the operator at the summit for Subaru last night, that was one of the things they were discussing, that the instrument they were using it's massive, it's huge, and if anything happened or needed to be changed, that switch would not be quick.
Oh,
No,
yeah,
Would
yeah.
not be quick at all.
All right, I'm going to see if I can try to pull this up, pull a couple things up simultaneously. So what we're doing right now, I'm going to sort of walk you through and show you a little bit about what's going on.
Oh, wow, look at this. This looks like a science image.
So we're looking, this is an acquisition image. So what we're looking at here right now is a GNIRS instrument, and we are setting up to do some infrared spectroscopy, which is what GNIRS does best. GNIRS stands for the Gemini North Infrared Spectrometer. It can do some imaging, a little bit of imaging in this little keyhole shape, but what it's doing, so the first thing we do is we will point the telescope at the part of the sky where we think the thing is. Look, there it is, we've got it. And then we need to line things up correctly. Oh, good, we're doing some IFU work here tonight.
And that's the integral field unit.
That's an integral field unit. So IFU spectroscopy is a really exciting thing. So usually sort of the base spectrometer, what it's going to do is it's going to take the light from a distant object and it's going to split it up. It's going to essentially make a rainbow out of it. It's like when sunlight passes through a prism and you get all those colors. That's what it does.
I see.
And sort of traditionally, you either do imagery or you do spectroscopy. But what the IFU does is it allows you to do both at the same time.
Oh,
so for example, what we see here is this is just the acquisition image right now, but we're going to get spectroscopic data in the main data frame here. But if you can reconstruct that data into a spatial image, and so you can see that same star right here.
Oh, and so in that other window, is that just to make sure that it's centered properly?
Correct, exactly. So we're going to go through our acquisition process. We're going to make sure that that star is lined up correctly. It looks like we're actually really close. We go through a couple of iterations of lining that up. I want to make a note here that the viewer that you see here is showing the image in shades of blues and yellows and kind of in greens there.
Mhm.
That's artificial color. That's fake color. The light that we collect that we're seeing here is essentially, I don't want to, it's not that it's monochromatic, but the detector by itself does not make the distinction of color. So it's like honestly, it's in this mode, it's colorblind. It can't tell color all by itself. In order to get a color image, you need to collect light with different colors of filters.
Different filters, and you all have lots of
We have a
filters.
whole lot of different
Yeah.
filters for each of our different instruments. All of them have different filters.
How many filter wheels do you all have? Because we were talking to Kentaro again last night. I believe Subaru has 3 filter wheels with 8 spots that they could use.
So it depends. I know I can actually pull up a demonstration here in a moment.
Okay.
But basically, it depends on the instrument. GNIRS has 2. GMOS has I think GMOS has 2. NERI had 3. There's a whole lot. And some of these are broadband filters. So, things with names like R for red, and it's going to let a whole lot of that long wavelength red light through. Or G or B, you can guess what those stand for. But we also have things that are very narrow band filters, and very what we call molecular line filters. So those are things that are going to look at H2. So this very particular wavelength that we associate with hydrogen. That red wavelength that we associate with hydrogen at 656 nanometers. And that's not, so we have those filters. We have visible light ones for the GMOS instrument, and we have, I keep raising my hand apparently.
I noticed you keep talking with your hands, and it keeps Zoom just thinks you're so excited.
I see you did put your Zoom hand
I've also
up.
noticed
That's
like you've been
funny.
doing this, and then like the thumbs up will pop. I was
Oh,
like,
my
yeah, Erin knows what we're talking about.
Yes.
But so anyway, when I get back to talking about this viewer, and we pick a color map that allows us to make distinction. We can set a black and white color map. I like this one. This one is usually very good for people who are colorblind, because you don't have that red-green distinction. It's the values match up with the color. The brightness values match up with the color. So it's very good for that. And I think, blues and greens and yellows is just pretty.
It is.
All right.
Really pretty.
So let me show you what we've got here. We started collecting science data here. And I'm going to come over here. This is our observing program. This is actually the program that's running right now that says we're going to adjust the telescope position slightly. We're going to do it. We're going to take our 2 15-second exposures and put them together. We're going to be using these gratings. We're going to be using the IFU unit. But basically what we're doing here is we've got 8 actual observations, and each one they're going to shift the position of the telescope around slightly. So you can see, here we go. This is our image. And this is the data frame that's collected.
That's the data frame.
That's the data.
Okay.
And we can reconstruct that into, here's our star. And so we're just basically just going to move around and put that star in different parts of the detector as we collect the data. And part of that is so that we can help us subtract out noise, but also part of it is because the detector gets tired. When you have a lot of light hitting a certain area of the detector, it'll get funky.
It's a detector. How does it get worn out?
Well, it's not that it gets worn out. It gets tired. If you go and you stare at the sun for a couple of seconds and then you stare away, don't do it.
Yes.
Your eye will have difficulty seeing in that spot. You'll get spots there, and it takes a while for that to recover. And so as we move our target of interest around on the detector, essentially we're directing the light just a little bit different each time. That allows the detector to recuperate.
I see. So to make sure that the detectors can continue to be efficient and give the best image quality possible.
Now, what I want to try to do here as we're collecting data is I want to show you, I'm going to do a little slice. So this is spectral data. And what I want to try to do, we'll see if this works with this particular data set. I am going to try to see if I can put a brighter one than that.
And while you're doing that, I know, Emily, you all talk about spectroscopy and spectra so much when you go out to, when you're in events, especially when you're out in classrooms, like we have Journey Through the Universe, the fall version coming up, and spectroscopy is always a really fun topic to talk about. How do you bring students into this kind of conversation with a basic definition of spectroscopy that maybe you can share with us?
So everything that we do here at our observatory is always studying light, and it's studying the nature of light, and everything that we currently know about astronomy comes from light. So what a spectra is essentially doing is so we often think of astronomy as those really beautiful pictures, but not pictures aren't actually useful for the science side of
That's
astronomy.
right,
It's
that's right,
great.
you're right.
It's great for bringing people in, but you don't get a lot of data out of a picture. You get more data when you can turn that light into a graph where you can be breaking up the light into its components and seeing what aspects of the light are most interesting.
That's
And
right.
yeah, and one of my a great description I heard about these detectors, about how they're so different from like a camera on your phone, is these detectors they're really set up to be detecting if something is there or not. It's a 1 or a 0. Is a pixel receiving light, or is it not receiving light? And that's why I think some people, when they look at this, that's the data that you're getting
That's
from an
it.
8-meter telescope.
Right,
It's like, no,
exactly.
but this instrument is really there in order for us to get down to the nitty-gritty details of, are we detecting a certain portion of light, or are we not? And then when we are able to detect that, we can detect things that are happening with the light. Say we are looking at a star and we know that star is using hydrogen as a fuel source,
Mhm.
but there might be other elements within the atmosphere of that star, and with the
Definitely.
spectra we can determine what other elements.
Right.
And then it's really fun if that star has a planet orbiting around it, and if by just chance that planet passes between us and the star, and now we got the light of everything that is in that star, and now we saw that light go through the planet, and now it's like, oh wait, now we can see what's in the atmosphere of that planet.
Right.
So if I can explain a little bit about this, you're seeing each of
Yes,
these vertical
please.
lines that you're looking at is a spectrum. And so you have one end of that spectrum at the top, the other end at the bottom. What that means is, if it was a visible light spectrum, you might think that you've got violet at one end,
Right.
blue, green,
Oh,
yellow,
yellow.
orange, red
Red, yeah.
to the other end. Now, this is infrared, so it's not those colors, but
Yeah.
basically this trace that you see here, this blue line that you see here, is a trace along this particular spectrum. And so you're getting, what we see here is you're getting some what we call continuum.
Mhm.
So that's light given off by something that's particularly warm, a
A
star.
star will do
Surface of a star, a surface of a star, like our sun, is sitting around 6,000 Kelvin. So, and then you also see not just a smooth curve, but you see lots of jaggies. And those jaggies, let me see. Oh, I gotta zoom the right way.
I was just going to ask that. Yes.
All these little jaggies, each point where this goes up,
Mhm.
that's a bright line. That's this bright line right here.
Oh, okay.
And so each one of those bright, where where you see those little peaks, represents some kind of element. In the visible spectrum, it's some kind of element. In the infrared, you're probably looking more at elements to molecules.
Okay.
Down in the radio, you're looking at molecules. But so what we can do with that is, as Emily mentioned, we can learn about composition. So
Yes.
if this were a transit observation, then we might look at this and say, we can see that, oh, there's water vapor in this atmosphere. We might see that there is carbon in this atmosphere. Basically, we can decompose that spectrum into learning something about composition of this distant place.
Absolutely. So as we go further down on this cut that you're
Yeah.
showing us, Aaron, we see, so of course we see those peaks, as you were saying, they're shooting up really high. But then as we get further down, exactly where your cursor is, we see what looks like an open portion of it where
Yeah.
it's not, the peak isn't
Yep.
up and cupped, but it's open, almost
the-
like an absorption line would
It's
look like.
yeah, it could be. I think in this case, we're probably looking at a lot of noise,
Oh.
to be honest with you. Um, but that may be an absorption feature. Most of the absorption features we're going to see when we're looking at a stellar source are going to be coming from absorption features of our atmosphere. So as that light passes through our atmosphere, some of that light's getting absorbed because infrared light does get absorbed by our atmosphere. This is why we have a greenhouse effect, which we like in small amounts because it keeps things nice. We don't like in larger amounts because it makes things bad. But that's, I mean, when we see that in a stellar source, that's usually what it means. There are ways to get absorption lines in astronomical sources, even in stars. If star has a very large extended atmosphere, we can get absorption lines off of that. But that's part of the reason. One of the things we have to do, say with this data, is whenever we are doing sorry for a second here. I am going to get us, I'm going to take a look here. They're setting up on another target.
How can you tell they're setting up on another
So if I
target?
come over here, I can see that we are working on a new program. And this is an acquisition sequence. And so they're going to take another field image here. And it's probably going to be another exciting star.
Another exciting star. Yes.
Every star is exciting.
Every star is exciting.
They are. This is true.
So we're going to see, I can tell that after sitting so many hours in that observing chair, I know that this is an acquisition sequence. And once they get done with that and they start the science, we're actually going to go over to the control room and talk to our night crew.
Exciting.
But so the thing that I was saying before that, which I have now completely.
Oh, well, you were saying that they're getting an acquisition image, and
Oh
then
yeah,
you
but
were
before
wanting
that, I was saying, we see anyway, we can decompose that information. We can find out composition. We can actually find a lot of information by, I know what I was doing. So because there are contributing effects from atmosphere, one of the things we have to do in association with each infrared image is we have to take a standard. So this is a case where we're going to point to a known star with a very well-known spectrum, either right before or right after we do the science, or sometimes both if the science observation is really long. If it's a 2-hour observation, we have to do before and after.
Oh.
We're going to look at a standard star and use that to calibrate so we can tell exactly what part of the features we see in that scientific data is coming from our own atmosphere.
And that gets subtracted out?
And that's going to get subtracted out in the processing phase. All right, I'm going to come over here and here's our acquisition field for this star. This one's a little, sorry, my scroll for my magnification is a little shady.
Oh, no.
But anyway, here we see our acquisition, our field image. And this is a lot more interesting than the other one. We've got our bright source here. This is the object we're actually lining up on. And I can tell it's one we're lining up on because it's close to the center. We've got a couple other sources out here. We're not interested in those. But I want to point out as well in this image, you see that there is a lot of other stuff. There's a lot of lines and things. So these are artifacts from the detector itself.
So is the detector just that orange rectangle, or is that
So
whole
the
blue part?
detector, the detector is that whole purple square.
Oh, it's the whole purple square.
So what we're seeing here, when we're doing acquisition with GeneEars, we're looking through, we actually have a little imaging window, and that imaging window we call the keyhole. And that's that rectangular box with the little hemisphere underneath it.
It looks like
that is sort of the imaging area for GeneEars. GeneEars is not designed for imaging, it's designed for spectroscopy. So it's not going to use that whole area for imaging. What we are going to do is we're going to use that little keyhole is enough for us to acquire, to center up that source, make sure it's lined up with the spectrometer, and then once we're satisfied, then we switch over, and you'll see that whole square suddenly becomes full of data.
That's it.
So right now, that whole purple area is the detector, but only a small part of it's being used. The orange box here just says is something that this viewer tool uses
Oh, I see.
to determine contrast levels,
Oh.
to automatically set the contrast level. All right, so I'm going to go on. So this is, this is another IFU image.
And this is still an acquisition
So
image.
they're still doing acquisition, but now they're
Try again.
I am so sorry. That was not to use, Gary.
So here you can see, so this is another IFU image. You can see that principal image, the slit image on the main screen now, that line, the dashed line all the way
dash line,
across.
mhm.
So each of those dashes essentially represents a row of data that's going to get reconstructed into this. And so
Ooh.
we can talk about that. That may be a little more involved,
Okay.
but we can reconstruct that into the small image that you see up here. And there's our star. That's the same star we just saw centered up in the keyhole. So once they are satisfied, so here's what they've done. They've taken an image, that gray line, thick gray line here indicates a pause. They analyzed it, they measured it, and now they're taking another one. So what you're going to see here is that this star is going to be it's almost in the center. This next frame, it's going to be dead in the center.
Okay, so it says 1 second there. So now it's reading out, and now we're going to have a new image.
And there we are, right in the center.
Oh, brilliant, brilliant.
So now Jesse is running this acquisition process, and he is going to go through that measurement process again, and the program will tell him, nope, you're lined up perfectly, start the science data. And so what we'll see here is the next science frame will pop up. There we go. And this is our next science frame. And this one's going to be a long one, and it's going to take us through the end of the night here tonight.
Ooh, how long is it?
I think
Where were we?
What
Is
do we
that
got?
280 seconds? Those are pending at the very top.
right. So what I'm going to do is I'm going to go, this is 143. I'm going to pull up something else here real quick because it's kind of fun. And I am all about, I just have to
Having
find
fun?
I just have to find the right window is the problem.
And while you're doing that, Emily, could you quickly describe to us, because there are different types of stars. Can
Yeah.
you quickly go through the different types of stars for us?
Oh my gosh, quickly.
So we have O-type stars, which
Oh,
are the
man.
biggest, largest,
Biggest, brightest. Yeah. If you don't mind me simplifying, sometimes
ahead.
I'll go, so you can oh man, yeah, how do you break up stars? I often, when I'm talking with students, I'll break up stars by going small, medium, large, or
Yes.
or
Yes,
tall,
please.
tall, grande, and venti.
And starting
so-
with our star, exactly, because many people don't realize that our sun was a G2V type star, which I'm sure
Yeah.
we'll talk about, but it's on the lower end of
Yeah.
that size scale.
Yeah, we're a nice medium. We're a medium to low, and
Okay.
honestly, in that area, like that's if you could pick what star you wanted to set up your civilization around, you want to go towards the lower end of the spectrum.
Okay.
Because in talking about that, like a small, medium, and large, the rule of thumb is so all stars are balancing it. So you have the gravity of the mass of the star that is pushing in, and then that pressure pushing in, that gravity of the star pushing in needs to be balanced by the energy being created by the star pushing out.
Mhm.
So if you are a smaller star, that means you don't have that much mass, so you don't have as much pressure pushing in, so you do not need to be producing a lot of energy in order to be pushing out. And so smaller stars tend to be more fuel efficient
They
and
last
will
much longer.
last much longer. The smallest stars in mass that we know of in the universe, called red dwarf stars, their estimated lifespan is so long we don't know what happens when they die, because
Really?
because those stars are so small, so faint, so fuel efficient. We estimate that their lifespan could be on the scale of around 3 trillion years. But if the universe is only 14 billion years old,
Right.
there has not been enough time in the universe for those stars to have run out of fuel yet. So the stars, those first stars that would have been born first after the Big Bang, they're still chugging. They're very faint. They're very hard to see because
Yes,
they're not
sure.
producing energy. But yeah, that's that lower end of the spectrum is where you want to be with that.
Right.
Mhm.
And it's kind of an interesting note because by one measure, we're sort of right in the middle, as you know.
Mhm.
But from when we actually count by size, we are by far the vast majority of stars are smaller than our sun is.
So
Like
this
92% of all stars are smaller than the sun.
92%
Something,
of
I think
all,
that's about the number. It's
most
been a
stars
little
are
bit since I looked up
smaller.
that number.
we're
Yes.
gonna go with you as the expert on that, Aaron. So
It's
when
90 something.
when we're looking at this star, how can we tell if this is a massive star or not? We can't really tell that.
We can't just from what we're looking at from what we're seeing here right now.
That's right.
But the spectra of these stars are different. And so what we can do, if we, once this data is reduced, we can compare this to other known spectra and we can see exactly what kind of star this is. And we can classify it that way. And that is our primary tool to classify stars. And in fact, there's a really, one of our nice tricks that we do is because, we study stars under known conditions where we can do things like we can independently measure their mass and their brightness and their spectrum. And then when we go out and we see a spectrum that looks like that, we know that it's got to have a very similar mass and a very similar brightness. And so then you can say, well, how bright does it look? Because if its intrinsic brightness is greater than it looks, then that means that star must be very far away. So you can actually go backwards and calculate distance data from that and figure out exactly how far away these things are and fill in that third axis.
Yeah.
Mhm.
Which is sort of one of the continuing issues in astronomy is to
Oh,
figure out
is
how
it?
far away things are.
It is.
Oh, it's definitely
Yeah.
locating things.
Since something that is faint and close can look very something similar to something that is bright and far away.
Right.
And so
Exactly.
it's taken us a long time, and by us I mean like a collective all astronomers across
Yes,
the
yes.
history
Taken
of
us a
time
while to get
in
that.
order to get some measurements to distance sort of thing. But the rule of thumb is the farther something away is, the less confident we
The
are
last coming are.
that we think that
That makes
that distance is fully accurate.
The uncertainty gets larger, but it's still a fraction of the total. So,
So it's not too. So it's reliable.
it gives us a good idea. Yeah, it is. You know what? It looks like we're in a good position. Let's see if we can throw this over to the control room. Hello, control room. I don't know.
Layla's not there.
Hello, Layla.
Oh, okay. I can't see it.
Yeah,
Hi,
they're
Layla?
conversation. I don't think they can hear us.
They're not. Shall I pop in?
You can or I can, either way.
I'll go.
Put your head in, yeah.
And we're gonna pin that.
Yeah, pin that.
Oh, it is. It says it's pinned.
I always do like my gallery view, so sometimes I don't see it. If it's usually if it's pinned, if I switch to the other view, it's in a spotlight. Maybe spotlight is
Okay.
Hello, control room.
Hello.
Hi, conference room.
Is your guys' mic on?
We're gonna need
Oh.
you to unmute.
We are unmuted.
We are unmuted. You,
Okay.
can you
We are
still?
unmuted.
Yeah, we can't
Can you
hear
s-
you.
We can't hear them.
Maybe
Oh.
because we have our speaker on?
You still show as muted. Oh wait, they don't show as muted.
Did we turn off the speaker for the big thing?
Yeah.
Can you hear us now?
This is the first time that we're talking.
So
No.
it shows as muted on.
Oh yeah, we turned off this speaker, didn't we?
channel, but we're not showing muted.
Oh,
so
we
I don't know
hear
why
you.
it's-
There's Jesse.
We got you now.
Oh,
Mike.
cool.
Okay.
Hi,
Oh, they
Layla.
can hear us. Nikki Johnson can hear us.
There
Hi,
you
hi,
go.
Nikki Johnson.
Hey, Nikki.
Thank you, Nikki, for the confirmation. Amazing. Quickly, could we introduce the new person in the room?
Yes, this is Hubert.
Hubert, go
Hi,
ahead.
Hubert.
Hi,
Introduce yourself.
Hubert.
Hi, my name is Hubert Conteretti. I am the CTO and Director for Software at NORLA.
Welcome. We're
Yeah.
glad to have you. We're glad to have
Our
you.
new big boss in engineering software IT ops, and he's coming to check out what happens at the ground level,
Oh,
Fabulous.
wow.
learning from each other.
Yeah.
Wow.
So everybody in the room deserves raises.
Well, he's not our boss, he's engineering's boss, but yeah.
No,
Yeah,
We do.
they deserve raises too.
Yeah.
I'll keep that in mind.
Thanks, Hubert.
Thank you. So Layla, Jesse, we've been following your work, what you've been doing closely here since you started the acquisition, and now Aaron, we were wanting to talk with you, Layla, right?
Yeah, we'd like to talk to both of you, the night staff. Tell us a little bit about what you're doing, and maybe if you can talk to us a little bit about the engineering work that was being done earlier, Jesse.
I absolutely can, yeah. So what we were doing and we were very busy with for the first couple hours of the night was we were working in our adaptive. I don't know if Aaron, did you describe to them what adaptive optics is? And
Yes, we did.
yes, okay. So if you have adaptive optics, you have some light going into the adaptive optics wavefront sensor, which is telling the deformable mirror how to move. But then you have the other half of the light going into an instrument, which has different optics in it. So because the instrument has optics that the adaptive optics doesn't have, there's always going to be inherent aberrations, deformities in the wavefront that go through the instrument. This is called non-common path aberrations, or NCPA. So what we were doing was working to figure out if we can correct some of those non-common path static aberrations that we get and make our image quality even better when we're using adaptive optics than it is now, it's already good. We're trying to tweak it and optimize it, basically.
Excellent. Thank you. Can you tell us a little bit, Jesse, how long have you been doing this? Not tonight. How long have you been working at the observatory here?
I've been here since April of 2007. So if you do the math, what is that, 17 or so?
Wow, Jesse. Yes.
Yeah, long time. I did not start as the manager, but yeah, I was operator. Back then we had separate operations and observers and stuff like that. So I came in as an operator, then eventually our groups merged, and eventually my boss retired and I applied for this position and now I'm here.
Okay.
In a nutshell.
Can you give us just a little brief view of how you got here? What kind of schooling did you go through? What did you do to get here?
Sure. Yeah, there's and we could talk to Layla as well, because there are so many
Absolutely.
different ways to get into telescope operations. It's operations itself. Now, if you're going into research astronomy or something, it's more of a track that Aaron would know more about that. But yeah, I started off at a small liberal arts college in St. Paul, Minnesota called McAllister. I studied physics, and then I had an advisor that was the astronomy and modern physics teacher. And basically, I fell in love with astronomy. I said, I want to do astronomy, but I don't like research. I like to read the research. I find the competitiveness of trying to fight for first paper and this and that. I found it really not my style. So I asking my advisor, and she told me, yeah, you can get into telescope operations. And I was like, sweet, that's what I want to do. And she goes, okay, and hand me the keys to my observatory at the small college. And that was the start of it. Yeah.
Wow.
Yeah.
That's
And since then
fabulous.
I did some school for optics and stuff like that. But basically, yeah, it all started undergrad school in physics and astronomy.
Fantastic. And Layla, your path here has been a little different.
Yeah, I like my path. So I went to a school in Daytona Beach, Florida called Embry-Riddle. And they're mainly a pilot school, but we also had a physics and astronomy department. So I majored in astronomy and astrophysics. And during my time majoring, I realized how much I didn't like school. So I said, okay, what can I do with a degree in astronomy, with a bachelor's degree? And I thought you had to have a PhD to be a telescope operator, but it turns out you don't. And when I applied to this job, I said, all right, I have nothing else to lose. And I got it. And then now I'm going back to school.
Great, and now she's studying while she's working.
Yeah.
No, we've
Working on
got, yeah, I
some-
don't know, Erin might have already told you guys already, but we've, in the operations group. In particular, we've got people with all sorts of different backgrounds, all sorts of different levels of educations. From bachelor's to PhDs. It just really is more about what you're passionate about, not about how many degrees you have.
Fabulous. Thank you so much. That's a really good, I think a really good view of those of a couple of different paths and
Yeah, no, it is. And it's, I think, very important for people who are with us now, who may watch this later, to understand exactly what you said. There are various ways to contribute working at an observatory, and it's not about how many degrees you have. It's really about what you're interested in and what you want to work on.
right.
And that, I think that's an important message to get out.
And I think the people who operate the telescope and the astronomers get all of the attention, but we have a lot of staff. We have people like Hubert here who are programmers. Hubert, can you tell us a little bit about how you got here? On a plane.
Yeah, I can. So, I got my degrees in computer engineering, computer science at the University of Southern California. And from there, I joined Microsoft. So if you use anything Microsoft, chances are you're using part of the code I wrote. Windows, Office, Xbox, OneDrive, a bunch of other products that way. And then I was at Amazon. If you use Alexa, you're again using part of my code. I worked at Twitch. If you stream any video games in particular, or just stream videos over Twitch, I rewrote half of that site, so that's part of the code. I used to work at Ellie Mae. If you bought a house, especially in the western part of US, that's what we worked on. I was at PDM, where if you bought any automobile parts, chances are you're using our platform. A couple of startups, and then from there, now I'm here. And kind of as you were mentioning earlier, one of the other aspects of an observatory is all the software that we need to run the telescopes. And currently, that's the organization I run, and a lot of the software, data, IT that we do in the organization is what I'm looking over at this moment.
Fantastic. Thank you so much.
Wow.
We have programmers, we have technicians, we have instrument specialists, we have welders.
Yes.
I think the number one requirement for working at an observatory is you need to be a problem solver.
Ooh, that's a big one.
You can't be a person that sits and stews and complains about a problem. You need to be an active problem solver. I think that's the number one.
Across the board, I think everybody here pretty much.
Exactly. Like everyone is a problem solver.
Very good. Thank you so much for that. What kind of science? Can you give us a little a description of what kind of science we're doing now? We've seen that we're doing some.
Yeah, I
some
can look it up
G-Nears
real quick.
IFU?
To be honest, I didn't read your abstract because we've been really busy chatting and.
You
and
guys
figuring
have
other
looked
stuff out. But
insanely
what we're
busy in there
doing-
all night.
yeah, we're using the G-Nears. I don't know if you guys have explained G-Nears yet at all, but we're using a low resolution integral field unit. So we're getting both spatial and spectral data at the same time. The title of this program is Probing the Farthest Supernova Remnant Interacting with Molecular Cloud H2. So, I'm not gonna go open up their abstract and waste a bunch of your
Yeah,
time,
no,
but we're looking at a
that's
supernova
fine.
remnant that's in the middle of a molecular cloud, and they're trying to get some spatial and spectral data on that.
Well, that's fantastic.
a
Yeah.
supernova remnant, so
So-
something like M1, not
So,
M1, but
Right,
something
so
like
we're
that.
looking at when one of those massive stars explodes, not like those little ones
It's
Emily was
not
talking
the
about.
red
It's the
dwarfs.
venti ones.
The ones that my research specialize in.
Ah.
Although I study the other end of their lifetime, I study their formation. But these stars are 8 times the mass of our sun or bigger. That's 8 times sort of the bottom limit of their size.
Mhm.
They are very rare, but they play an outsized role in galaxies, in essentially in the entire behavior of galaxies and other stars. So we've got a star, it reached the end of its life, it exploded, and it threw off all of this material. And that
Mhm.
material that was ejected is called the supernova remnant. And because these massive stars, they're forming in a nebula which are gas rich, by the time they die, they're still in that nebula. And so as that cloud of debris from that explosion expands outward, it's going to interact with the nebula around it, that hydrogen rich gas, and it's
Yes.
going to cause shocks in that gas. My particular area of research, this is great. I get to talk a moment about my
Yes,
research.
yeah.
One of the things that I was studying was what happens when that shock front from that supernova impacts some of the denser parts of that cloud. And the idea is that it can pile up some of that gas and can trigger collapse and actually form additional massive stars. And so you have what's called sequential star formation, because you get one that goes, and then as it explodes, it sort of pops everything around it, and they keep working their way out. So I'm kind of, this is,
This is the
whatever this
first
is,
time,
that's the kind of
yeah.
thing that but I don't know if this is looking in particular at that kind of star formation. Infrared spectroscopy, this near infrared spectroscopy is not great for looking at star
see.
formation,
I
but it
see.
is going to be good at looking at that remnant and the dynamics of that remnant as it expands into that gas.
And so when you're thinking about the expansion of the gas and the
Yeah.
supernova remnant, what could, of course, the data for those of you watching and maybe watching later, the embargo is this data is embargoed for a certain amount of time, and of course we have to be very careful to not reveal information about anyone's science besides something general, no names, no exact things or anything, because that's very important that they have priority to get that data and use it and
Right.
publish within a year or two.
Right.
But generally speaking about supernova remnants, what could
Right.
be some motivations behind studying an object like that?
So again, from my perspective, learning how one of the mechanisms that might be responsible for additional star formation is a huge motivator.
Yeah.
But we've got a universe that started out with 3 ingredients. Hydrogen, 75% of the universe is hydrogen, 25% is helium, and a tiny, tiny, tiny fraction of 1% was lithium. Not enough
Ooh.
to worry about. Hydrogen and helium is it.
That's it.
But when we look around us, we see very little hydrogen and helium. And in fact, all the helium we see is later developed helium, not the original helium. The
Okay.
helium in your balloons is not some
For
of that
sure
original
not.
helium. I mean, some of it might be, but
Most of it's not.
most of it's not. But the things you look around you and see, I look around the room here. There's
Mhm.
carbon in the wood of the table. There is silicon in the cinder block. There are all of these different elements. I look at Emily and Jamaica, and there's carbon, hydrogen, oxygen, and nitrogen.
Yeah.
Chomp, and a little bit and phosphorus. Chomp. And so you look at all this stuff that makes up the world around us, and and us. All of that stuff. None of that stuff was here at the beginning.
And so stellar nucleosynthesis.
Stellar nucleosynthesis that occurs at the end of those massive stars' life is responsible for a lot of that. And in fact, all of the elements, we think that basically all of the elements that's not hydrogen and helium come about through essentially through a star's life and end of stars' lives.
So with this supernova remnant, would that explosion that would have happened to create this supernova remnant, would those elements be found there in this
Exactly.
stew of gas and
So,
dust?
you think about this nebula that starts out and it's
Yes.
got that 75-25 hydrogen helium ratio. That's all it is. But when those supernova explode, you've got this massive debris cloud of all this other stuff that is rushing out into the nebula and merging with the nebula. So that, when I mentioned that shock wave may trigger the collapse of a pre-collapse core. You've got some tight knot of gas that's sitting there just sort of at the edge of stability, and it gets that shove from that supernova shock wave. And not only does it get that shove, but it gets a bunch of those massive elements as well. And so when that collapses and it forms a star and it forms planets, it's not just hydrogen and helium this time. It's hydrogen and helium and oxygen and carbon and nitrogen and a whole bunch of other things. So we actually can look at these stars. Emily was talking about one way to classify stars as small,
Small, medium, large.
small, medium, venti. Yeah, right. But another way of classifying stars is by their metallicity.
Oh,
And to an astronomer,
that's right.
metallicity, it doesn't mean what you might think of when you think of metal. To an astronomer, metal means anything bigger than any atom that is bigger than helium. So to the astronomer, lithium, oxygen, these are all metals.
I love
metals. I know, I love it too. Astronomers count one too many hydrogen helium metals. It's basically just like that.
That's a periodic chart that most people can remember.
You think about the very first generation of stars that formed, the very first, they're just hydrogen and helium and nothing else. So if you were to look at their spectrum, they'd be really boring. There wouldn't be any of those sharp lines. You wouldn't see those strong features. But as you get to second and third and fourth generation stars, these are being made up of some of this material from these high mass stars that exploded. They're being made of some material, smaller elements that come from lower mass stars that were blowing the stuff off in essentially in solar winds, in thermal events toward the end of their lives. Our star will chuck a bunch of carbon and oxygen out, in 5 billion years when we go. But each successive generation is going to have more and more of that stuff.
Wow.
And that means that you're capable of forming planets at some point that have where you might have a solid surface, where you might have rock, where you might eventually get life. So supernova are, those of us who study these high mass stars, we know that these are the tiniest fraction of a % of all the stars. But because they are so bright, you can see them from across the galaxy. And this role that they play, both in triggering new star formation and in seeding the galaxy with these larger elements, is outsized. This tiny little fraction of stars just impacts everything.
It really absolutely does. Can we look at that, our image as we close out? We're just a minute over our time, but I would really...
Oh, the current data?
Yes, the current data.
Supernova coming in, the supernova remnant. After we got the full context of why this is so interesting for us to be studying.
Supernova
absolutely.
remnant. And I mentioned M1 Messier 1, and I wanted to make sure I clarify that was Messier 1, Messier objects, for those of you who may not know what that M stands for. And things have changed here, Aaron. What's happening?
So we are looking at, I have, all right, so the last step that we took, the one that we're seeing here, is an unguided step. So we're not actually looking at the science target itself. We do a lot of on-off observations. So let's see if we can I'm gonna try to be, I'm gonna see if I can be clever. We are, and I think part of the problem here is we are looking at a very faint source. So we may not actually see it here, but let me try one more thing before I give up.
Okay.
I am going to see if we can do a little subtraction. If it doesn't break the program. Come on. Oh, set. Hit the right button. All right, and then we're gonna go previous.
Ooh,
Okay. So what I'm doing here in this image is a very base subtraction where I'm subtracting one frame to the other to try to get rid of some of the noise. Not seeing anything there. So, again, if we're looking at a supernova remnant, the remnant itself, after a few months, that remnant itself is not going to be radiating light very strongly. So it's quite possible we're just looking at a part of that remnant that we're not able to see easily here. But through the data analysis steps, the astronomers will be able to tease that data out. They're looking for very faint things.
Very faint, very faint. Well, this has been a really informative session, and I believe this may have been our very first Shadow of the Scientist session where we overlapped with an engineering
test. Sure.
So it was really great to feature, and I have to say that I'm really looking forward to our next session. But you all have what's called a shutdown coming.
We have shutdown coming.
And this is planned. It has nothing to do with anything external, but about the internal operations of the observatory.
So every year we do an engineering shutdown. Each day our summit crew are this amazing group of technicians and engineers. They go up to the summit almost every day, usually 4 to 5 days out of the week. And they are doing maintenance. They're doing, they're working on all these different tasks to keep the telescope running. But there's a lot of things that require very intensive work. And so once a year, generally for a few weeks, we go through this engineering shutdown. We shut down our systems for a few weeks, 2, 3, 4 weeks maybe, and we disassemble parts of the telescope. So that instrument, we pull all the instruments off. We pull the instrument support stage off. We pull the acquisition and guidance out.
Everything.
And so then we can do all of this maintenance that we can't really get to when the telescope is all put together. So this has nothing to do with the government shutdown.
That's exactly what I wanted to make sure you said. Yes.
Nothing to do with the government shutdown. We are still in operation. We're still going along just fine here so far. But we go through this engineering shutdown, which means we won't be on Sky for a few weeks here. And actually, I'll be back in the control room when we do go back on Sky. So when everybody's enjoying Halloween trick-or-treating, I'll be here.
Well, between now and then, we have something that I kind of spoke about earlier. Journey Through the Universe is going to be happening in October and fall, and we for the fall portion of it, and we have a new guest who just joined us. Emily, would you like to introduce her?
This is my boss. I'm gonna remove spotlight off the control.
Oh yeah, please. Sorry about that.
Now we can actually see our room here. And this is Leilani Mlozi, the Education Engagement Manager here at Gemini North Telescope. So our team here with Education Engagement, we facilitate and organize educational engagement programs across Hawaii Island, including Journey Through the Universe, which is just coming up. It's a year-long program, but we do have some weeks of higher intensity programming with it, and one of those weeks is coming up pretty soon.
Yeah, so Journey Through the Universe, right, 22 years old, in partnership with the Department of Education here in Hilo, Maunakea. So we visit all of the schools in our complex area, all of the grade levels over the course of a year, and we have Fall Journey Week, which is the first time that we're ever doing classroom visits in the fall. They're usually all in the spring, where we see over 200 classes, about 4,000 kids in 1 week. And we're now, in addition to doing the spring journey, doing fall journey, so that we can visit these students more than just one time a year and hopefully build upon that foundation of knowledge that they get in each classroom visit. I'll also give a little shout out to my mystery pop in right now
I was
has happened
serious.
is that we are doing a fall internship right now for local high school students in partnership with Project Hokulani and the CLD teams at UH Manoa. And so we have 3 high school interns right now who are experiencing absolutely everything that you could experience on Maunakea, from like telescope operations to we were watering a bunch of native plants today, and then learning how to operate the smaller telescopes at the visitor center. We had an amazing view of the sky tonight before the very bright moon.
Yeah.
Which was
Bright
also,
tonight, yeah.
like, amazing to see.
Oh, the
like,
moon
that
is always great.
And so by the end of the week, they will be selecting the next astronomical image to be imaged by the GMOS instrument here at Gemini North Telescope into like a beautiful poster that's going to be shared with all of our local students for like the next 10, 20 years. So yeah, Project Hokulani is really cool. If you're a high school student, if you know high school students in Hawaii, this program is across almost the entire state. They have different internships on almost all of the islands. Yeah.
Incredible.
You know, Leilani, you mentioned getting these opportunities to help teach students. I think one of the things that I really appreciate as an educator is not just what we're teaching them, but the relationships that we're building with the community. And I know that I have had a lot of people that I have seen in, kids who will come up to me, they see me in public on a couple of occasions, say, I don't know if you remember me. I was you came to see our class last year. So just building that relationship, nurturing that relationship with our community.
Yeah, we're definitely not teachers here because God bless our teachers, like, and the amazing jobs that they have to do. Almost raising all of
Absolutely.
our kids, right?
Absolutely.
But with programs like Project Hokulani and being able to build these internships where they're not just learning about astronomy or science, but actually having experiences on Mauna Kea, learning about various perspectives of the sky and of our sacred mountain is so amazing. So it's really, we're just like guiding,
Yes,
and what they learn, that's their own decision.
Wonderful. And so we have here from Nikki Johnson. That sounds like an amazing program. Thank you, everyone, for another great session. Oh, it's 3:40 a.m. for you. Yes,
Oh, man.
Nikki, thank you so
Great.
much.
Staying up with us.
Yes,
It's almost
thank
time for me
you.
to go to bed.
Yes, we're almost there. Thank you, Leilani, for stopping in. Well, stopping in. When I waved you in, I'm glad you came over to share with us not only about this incredible Hokulani program, but also to speak a bit about Journey, because we did reference it earlier. So perhaps Emily, in our November session, you can talk a bit more how it went. If you're available, you can perhaps join us.
Yeah. Thanks for having me. And I'm gonna go home to my 1-year-old baby.
So thank you. This is a great way to wrap
I
up.
think so.
Thank you all for joining us. It's so good to see you. Thank you all for joining us. And in the control room, Jesse, Hubert, Layla, you are amazing. And I know our new guests, we kind of put you on the spot and you just flowed with it. Thank you for sharing with us. Your contributions are very much appreciated. And I'm going to bring it back over to Emily and Aaron to close up.
Fabulous. Thank you, everybody, for staying with us tonight. We got a 2-hour session in tonight. It was a lot of fun to be able to bring all this to you and show you a little bit of what's going on. And I look forward to seeing you next time.
Yes, definitely.
Thank you for your questions. Thank you for being curious. Your curiosity is what helps us
Absolutely.
be able to do this and helps us keep our jobs too. Just curious about the universe in a general sense. So what we're here for.
That's right. So stay on top of our upcoming sessions. Check out our Shadow the Scientist website to register. If you have any questions, you'll see how you can also email me and my colleagues to set up either sessions for your group or to join one of our open sessions. Until then, keep looking up. Thank you, and we'll see you next time. Aloha.
Aloha.